Yeah, in this lecture, we are going to talk about altogether a new area again, which is known as the wear debris analysis. Right in the beginning of this semester or this lecture series, I had told you that usually condition monitoring is done by vibration. Then we had a technique called wear debris analysis, which is nothing but the contaminant analysis, and 20% of the cases in the world actually use wear debris analysis, wherein they analyze the lubricating oil and find out the properties of the oil, and also get a clue as to the failure mechanism or the wear and tear mechanism the machine, because by studying the composition of the debris which have got deposited in the oil. Tribology is nothing but the study of friction, lubrication and wear. So, what happens? You will all realize that when we are talking about machines, maybe two members are coming in contact with each other, but these surfaces are really not smooth. So, there are some asperities, and to reduce the friction, we put a layer of lubricant, and because of this force, and they could be sliding. So, this mechanism of sliding under the application of pressure, maybe another thing is one is softer material, one is harder. So, while you design a machine, you will come across such scenarios. So, what happens? Because of forces, because one being hard, one being soft, because there is surface roughnesses, there is a lubricant, on top of it there could be corrosion, corrosion on the surfaces, there could be abrasion, there could be adhesion. These will give rise to these surfaces wearing out. Wear out occurs. So, where do these wear particles go? So, the wear particles will get deposited in the fluid medium. In this case, the fluid medium is lubricant. So, in the process what happens? The lubricant also gets spoiled, lubricant, or we can tell it as oil. So, the oil will also get contaminated. So, the oil's properties would change. So, we will study about the oil properties in the next lecture, that is on oil analysis. But even these wear particles, because they have worn out from a parent material, this is my component, machine component. And this because of friction and wear and etc., these particles are flaked out. So, these are the wear particles, and they will get deposited in the oil. So, studying these wear particles, their chemical composition and their size, their morphology, their quantity, So, all of these give us a clue as to what is the condition of this machine from where these wear particles have come up. And this is essentially what we are going to study, what is known as wear debris analysis. So, this need not be done real time, though recently some developments are happening to do wear debris analysis real time by focusing on a camera system, looking at the images of the wear particles and doing an analysis in real time. People also can get an idea as to wear debris analysis. But for our sake of discussion, we will say that all you need to do, suppose I have a large gearbox, there is a gearbox on the outside and there is lubricating oil. By now we have studied, but by putting a vibration transducer and doing a real time signal analysis in situ measurements, I can find out faults. But sometimes it so happens these gears will wear out and they also, these wear particles will get deposited. So, the oil gets spoiled, but looking at this, the chemical composition, the size of the wear particles, the shape, the quantity, we can get a clue as to what is the condition of the gearbox, and this is usually done offline. So, who does this? So, in fact, wear debris analysis, it all depends on, all you have to do is collect a sample. Sample is collected and then we can, if we are looking for wear debris, we will look into these particles under microscope. Sometimes the particles are so small that microscopes are not good enough. So, we have to look under a little high magnification. Okay. And then how do we also need to know the chemical composition of these. In fact, you know every compound or sorry every element when heated or ionized the electrons will jump from an orbit at their characteristic frequencies. So, if we have a spectrophotometer which can measure the energy of this electromagnetic radiations at that characteristic frequency, I can know what kind of chemical element is there. So, such devices are known as spectrophotometer. So, one is an atomic emission, another is the absorption. So, AES and AAS. These are very costly lab type of equipment. So, they cannot be carried to the field, and so other ways we have to get that oil sample in which these particles are suspended like a colloidal solution. And we can see the chemical compositions. Characteristics, one is the quantity. So, how do I know the quantity? There are devices by which we can see the particle count in terms of by laser devices we can measure the particle count through an optical technique. Suppose I have a particle and then there are particles suspended in the fluid. If I shoot a laser beam and depending on the size of these particles in a given volume, the energy will get reflected from these surfaces. So, I can have a clue as to the particle count in a given volume. So, parts per million of a particular size. So, such particle count meters are available, which can give us an idea as to what is the amount of particles of a different sizes. So, we can have a filter, allow a light of certain diameter to pass through and so on, a light beam, and then if this quantity changes with time, ppm with time. So, this will obviously give me an indication that a high rate of wear is occurring, as opposed to this. So, this is we can have an alarm conditions, and this is not real time. No, maybe this is 1 month, every month or every quarter I am doing this, because they are expensive. We cannot. So, all I do is every quarter of a year I pick up the oil sample, do this particle count, and if I see that this high rate of wear is increasing, the parts per million is increasing of a particular size, I know something is going wrong with this gearbox. So, this is just to give an example how wear debris help us get a clue as to the wear rate and as to what is wrong with this machine, severity of the defect. Is it suddenly wearing very fast, or if there are any foreign components, for example, a dirt has got into the system. And of course, the wear particles, some particles we will see later on, some are circular, some are like plate, some have sharp edges. So, this also gives us the morphology, gives us an idea as to the type of wear. And composition, suppose we are talking about a journal bearing. This Babbitt material has maybe lead or tin, etc., or copper. So, if I see a high rate of maybe copper increasing with time, I know which it normally should not be, I know my bearing lining is wearing at a higher rate. So, these kind of observations can very specifically to a particular element only be done with wear debris analysis, because if you think of a journal bearing monitoring, at most I can measure through vibrations that the clearance has increased or decreased. The gap has increased or decreased through an eddy current probe. If this gap has increased, but the composition, element composition can only be done through spectroscopy. So, coming back to the discussion of atomic absorption spectrophotometer. So, in this we can measure all the elements which are coming out of this spectrum depending on their element, maybe copper. But the atomic absorption spectrophotometer, which can be calibrated to know the actual amount of the particular element. So, you will get a qualitative assessment of the type of elements present, but in atomic absorption which is calibrated, I can get a quantitative estimate of the type of element present in the wear debris samples. So, by now you get a feel that in machines when there are basic pairs, this kind of wearing mechanisms can occur. This is my lubricant layer. So, there could be adhesion, there could be abrasive or cutting wear, delamination, fatigue. Of course, delamination occurs in composite materials, fatigues, corrosion or oxidation wear, and electrical attack, acid attack. Okay. So, all these will lead to particles getting deposited in the oil. So, we will looking at the particles get a clue size, shape, quantity, and of course, the composition will give us an idea as to what is wrong with this machine, and this can be done in a very timely manner. So, some of the wear-in modes, you recall the bathtub curve. With time, wear rate, and which we have defined this as the useful life period. So, the initial run-in where we have one high wear rate, okay, and towards the last time or the end of the life of the machine, we have a high wear rate. Okay. And you will see the surfaces, there could be pits develop, there could be scuffing, and sometimes also there could be foreign particles. Usually silicon, because the silicon dioxide, sand, dirt, okay, they can get trapped in the lubricating oil because of very bad environmental conditions in a dusty environment. So, for example, in a coal mine, a cement plant, in a material handling plant, raw material handling plant. By the way, in all these plants, the bearings are actually sealed. Okay. So, seals form on bearings, because imagine I have a bearing and one foreign particle gets trapped, hard, sand, grain. So, this is going to score the races and it will form a lot of pits. So, this has to be avoided. So, if I somehow this silicon has entered, if I take the oil or the lubricant and do a AAS of that, I can find out whether silicon is present. So, I know in a metallic compound I had iron, maybe some alloying element, but I will be wondering where from the silicon came, because to begin with the parent machine did not have silicon. So, how did it come? So, this is where AAS or spectrophotometry helps us finding out these chemical elements. So, depending on the wear particle type, there will be different sizes of this. Some are the cutting, spherical, or rubbing wear. Typically, the sizes are very less. Maybe to our if you rub in your hand the oil, you will find that it is feeling rough. Okay. So, this roughness is because of these wear particles are getting in the oil. So, to measure them we have to look under microscope. Sometimes high magnification is required. Of course, I do not recommend scaling electron microscope, but if the sizes are less than 2 micron, maybe SEM can be used. Now, depending on the type of the particles, for less than 2 microns we can do spectrophotometry, and more than 30 microns we can do just particle count. Sometimes inside is known as a ferrogram, but this is only good for ferritic or iron surfaces. So, normal rubbing wear will be having flat plates less than 15 micron, severe sliding wear, flat elongated particles greater than 20 microns with striations, cutting wear, long curled strips of metal, gear wear, flat striated particles and so on. Okay, bearing wear, laminar pitlets, piers, small particles less than 5 microns, black oxides indicate insufficient lubricant, rare oxides indicate water contamination, corrosive wear, heavy concentration of fine particles, aluminum wear, white metal particle, dust or dirt, foreign particle or material not characteristic of machine or oil. So, these, as I was telling you, very important words: size, shape, quantity, composition, help us study wear, debris, and this gives to clue as to condition of the machine. See, unlike the vibration monitoring, where you required a very trained signal processing person or a software, here in wear debris analysis, all we do is just collect the oil sample, give it to a centralized lab, and they will do all the tests. So, this is like a human pathology lab, pathology of the machine. Okay, like you give your urine and blood sample for analysis. Similarly, here we give the oil sample where we look into the wear particles. So, some of the wear debris analysis methods, optical or the filter blockage. So, of course, there are also thin film sensors used to monitor the wear. Radioactivity is also being used, and magnetic attraction because it is a ferrography. Okay. Some of the spectrometric techniques used for debris analysis, I just mentioned to you: atomic absorption spectroscopy or atomic emission spectroscopy, XRF, okay, XRD, ICP, DCP and EDX. So, these are some of the machines, spectroscopy machines, which are used for doing the analysis, but mind you, they are very, very costly. Couple of them could run to a few crores or few less than a crore. So, these are very costly equipment, and every plant need not have such machines. So, all you need to do is sample your oil and send it across. So, some of the elements in spectroscopy analysis we must know beforehand, that these are the typical wear elements which we will find in any oil samples, and some of these additive elements are used because of the composition, and then the contaminants, silicon is the most, sodium and so on. So, we need to have an idea from a materials point of view that every machine component or the what is parent machine component, what is the material composition. So, this will give us to a guide that if I see maybe copper, I know in a machine, in a gearbox I see copper, well I will be wondering, in my first class perhaps there is no copper. So, where did this copper come from? Maybe the journal bearing in some bearing has copper because of the lining, and then this copper came about. So, typically wear elements, and they are found in pistons. Aluminum is found in piston, chromium in a lot of these valves, etc., copper in bearings, bushings, iron. Of course, every mechanical machine components has a good amount of iron. Lead is used as an additive on bearings, molybdenum as an oil additive, nickel for hardening the surfaces, valve guides, plating, silver in anti-friction bearings, shoulders, tins and bearings, silicon in just a dirt and sand, gasket sealant, oil, anti-foam and anti-freeze additive. So, we can come down to the elemental level by spectroscopic methods, and so all we have to do is the amount of this element present in the lubricant or present in the oil because of the wear debris particles, and how it came across into this system is what we need to study. So, if you see the typical metallurgy, rest all being iron here, bearing cages usually copper and zinc, rolling element bearings there is some amount of chromium and manganese, gears typically iron, shafts iron, gearbox casing iron, but these trace elements, for example, I see in a gearbox I see traces of molybdenum, okay, or I will see traces of nickel or nitrogen. So, I will know that some component has failed, and if you go to my book Machinery Condition Monitoring Principles and Practices, you will see the details in this website, few case studies wherein through a chemical analysis we have found out the composition, and we can indicate whether the material to begin with was inferior. A particular amount which should not be there was present, and this also helps us. So, some of the examples of contamination are mining, process plant, quarry. I was talking about quarrying, stone dust, water, mill scale, dust, water. So, all these components will get deposited in the lubricating oil, and then later on we will see how we can select this lubricating oil so that these contaminants do not get picked up, and then we do not get a wrong indication, okay, of like a false positive that something has gone wrong. Okay. Thank you.